slide 19 to 24. We will start with the data.
I will cover the so this is functional concept. So the advantage of functional concept is first, it shows its ability to measure radiation intensity and provide useful information. And second, able to discriminate between alpha and beta factors. And third is detector. Large area detector can be constructed. And then this advantage of proportional counter is efficient analog wire delicate and low efficiency in gas flow due to the deformation. And second, the efficiency and operation are affected by entry of oxygen to fill gas. And second is damage. Measurement window easily damage in large area. So next I will go to
okay. Just now the group has presented about the proportional counter. So my part here is the proportional counter where the secondary ion accelerated. So you can see the large one is alpha, the smaller one is beta. Next. Okay, this one is the schematic diagram of the proportional detector. Okay, next. Okay, the real diagram I will explain. Okay, you can see. Okay, you can see. See. Okay, here. The anode. Anode is the thin metal wire. Okay, so the anode will have the highest field strength. Why? Because the electron all will go inside here. Then the cathode is the cylindrical outside. They will arrange in coaxial manner. Then we have voltage source. Okay. Then lastly we have the electric circuit. So slide before. Okay. So why got the window? Window is for like low penetrating radiation will enter through the window, but the high penetrating radiation will enter through the cylindrical side. Okay? Okay, next.
So moving on, so I will continue the part B for the proportional counter. So as a comparison from the previous slides that's presented by Trevor. So here is a diagram for the gas flow system with a slope threshold. So what is the difference between the previous diagram shows by Trevor? So here we have a connection from the gas inlet and then connect to the gas outlet, and then we will have a threshold. So this is the anode. So it actually is a function at the center of the proportional detector. So next. So this point already we explained. So the anode is placed inside a cylinder. So as the previous diagram, and also the emission. So this actually is called two-high gas flow proportional counter, which shows in this chart. So what is the difference between the previous I showed you all and this picture? Actually is the difference is the shape of the proportional counter of this. So compare with the straight shape of the anode. So the strong anode actually will provide a stronger electric fields throughout the counter volume. So actually it will shortening the electron collection time. So from the previous pictures that I showed, actually we have a sample that insert in the bottom of the gas flow system of the proportional counter. So actually this is to minimize the amount of the air it produces. So and this gas flow system actually is operated at one atmosphere pressures of fluid gas which flow continuously, and then the common mixtures of 90% of water and 10% of the methane will be introduced in this system, and it is known as the P-test. You can spell for me. Thank you.
Okay, a very good morning to everyone. So I have a question. I will be explaining on the ionization chamber. So this is basically the simplified diagram of the DC ionization chamber. Okay, just a small recap because the previous group has already presented on the ionization chamber. So what is ionization chamber? Ionization chamber is those detectors that are based on the principle of excitation or ionization of atoms. And when the charged particles passing through the metal, they will leave along their path a chain of ionized or excited atoms which can be detected and counted. So how the ionization current is resulted is based on when an electric field is maintained across the material. So this is basically the DC ionization chamber, the introduction. So when an ion chamber operated in direct current mode, the negative charges can be collected either as free electrons or as negative ions. And the air usually used in DC ionization chamber is filling gas. So the typical ionization currents in most applications are very small, likely 1 picoampere or less. Thus, the leakage current through the insulator can perturb measuring the ionization current, where the perturb is mixed by the subject, either a system, a moving object, or a process to an influence tending to alter its normal or regular path or state. Next. So, the ionization chamber is the simplest type of gas field radiation detector, and it's widely used for the detection and measurement of certain types of ionizing radiation, so including the X-rays, gamma rays, and beta particles. So conventionally, the term ionization chamber refers exclusively to those detectors which collect all the charges created by direct ionization within the gas. And the gaseous ionization detectors include ionization chambers and devices that use gas multiplication. They are namely the proportional counter and Geiger counter. Next. So, ion chambers have a good uniform response to radiation over a wide range of energies and are the preferred means of measuring high levels of gamma radiation. And they are widely used in the nuclear power industry, research labs, radiography, radiobiology, and environmental monitoring. So, next I will proceed with the principle of the operation of DC ionization chamber. So, how they operate is a gas ionization chamber measures the charge from the number of ion pairs created within the gas caused by incident radiation. So it consists of a gas-filled chamber with 2 electrodes known as anode and cathode. So the electrodes may be in the form of parallel plates, the left diagram, and or a cylindrical arrangement with a coaxially located internal anode wire, which is on the right hand side. Then proceed with a voltage potential is applied between the electrodes to create an electric field in the field gas. When the gas atoms or molecules between the electrodes are ionized by incident ionizing radiation, the ion pairs are created and the resultant positive ions and the dissociated electrons move to electrons of the opposite polarity, which is means that positive ions will move to the negative electrode, which is the cathode, and the dissociated electrons will move to the anode, which is the positive electrode. Then this generates an ionization current which is measured by an electrometer circuit. Okay, so what is electrometer? The electrometer must be capable of measuring the very small output current, which is in the region of femtoamperes, 10 to the power of negative 15, to picoamperes, 10 to the power of negative 12 amperes. Depending on the chamber design, radiation dose, and applied voltage. So each ion pair created deposits or remove a small electric charge to or from an electrode, such that the accumulated charge is proportional to the number of ion pairs greater enhance the radiation dose. And this continual generation of charge produces an ionization current, which is measured the total ionizing dose entering the chamber. So, the electric field is now sufficiently strong enough to enable the device to work continuously by mopping all the ion pairs, so preventing the recombination of ion pairs, which would diminish the ion current. So this mode of operation is referred to as current mode, meaning that the output signal is a continuous current and not a pulse output, as in the cases of Geiger-Müller tube or the proportional counter. So because of the number of ion pairs produced is proportional to the energy of the incident radiation, this continuously measured current is proportional to the dose rate and it deposited a unit time in the ionization chamber. So last slide of my part is that referring to the accompanying ion pair collection graph, it can be seen that in the ion chamber operating region, the charge of a collected ion pair is effectively constant over a range of applied voltage. As due to its relatively low electric field strength, the ion chamber does not have any multiplication effect. So this is in distinction to the Geiger-Müller tube or the proportional counter, whereby secondary electrons and ultimately multiple valence greatly amplify the original ion current charging. So that's all from me. Thank you.
Belum lagi,
Today I am presenting about the Geiger-Müller 5. So this is the fun fact about the radiation, which actually the radiation exists naturally, and we do have background radiation, which is 0.2 microsieverts per hour, and the SI unit for nuclear radiation is in sieverts. This fun fact sourced from the a documentary from Uranium Twisting the Radio State in 2015. So this is fun fact originally originates from that documentary. Yes, that is the physicist that made the documentary. Okay. So this is the real picture of the Geiger-Müller counter, which is this one is the traditional one, and this is the portable Geiger counter, which is you can see here is rechargeable, and it is used to detect the nuclear radiation levels, which is alpha, beta, and gamma, and also the unit SI unit is sieverts, which is SB. Next, the next part will be explained by Humayra.
So this is the schematic diagram of Geiger-Müller. So as you can see, Geiger-Müller consists of metallic tube, and inside it has the gas medium that consists of 90% of argon and 10% of ethanol. So at the center is made of the electrode, or center electrode that made of the tungsten, and it connected with the positive terminal of battery, make it as the anode. So the negative terminal of battery will connect with the metallic tube, make it this metallic tube as the cathode. And then we have this RL that can count the potential drop. So this is the switch, electronic switch that consists of amplifier and power counter. So electronic setup is used to determine any potential drop that happens across the resistance, measure the associated amount of power path, and measure the amount of current over a period of time. So when we have one particle, external particle of alpha, beta, or gamma, come inside and complete the circle, there is one count here represent one external particle. Next. So this is the principle of Geiger-Müller. So what happening is the ionization of the external particle. So this external particle enter in the medium and collide with the matter medium or argon gas and transfer its energy to the molecule of the matter medium. So what happening during the transferring of energy is that this electron at the outermost shell of the molecule will absorb the energy until it has sufficient energy to free the electron. So at the end of ionization, we're going to produce one free electron and also a positive ion. Next. So we look on the function of battery and see what it can be done on the free electron. So this battery is highly potential difference that can create the electric field. So just now when we produce the free electron, it will subject it to the electric field to undergo secondary ionization. So this secondary ionization we call as Thomson avalanche. Next. So during the Thomson avalanche, there is an acceleration and deceleration of free electron. So when some of the free electron is subjected to the extremely high electric field, this electron will accelerate downwards. As you can see, it moves downwards to the center of the electrode and it capable for the secondary ionization. So this is what happening during the first ionization, and when it comes to the center of the electrode, it undergo the secondary ionization and it produces the original free electron and also new electron, and this happening continuously, rapidly. Okay. Next. So some of the free electron also will collide with the gas that accumulated at the center of electron and ionize the gas molecule. So what happening during the ionization is they can interact with the potential field of the nucleus that make the gas molecule be excited and experience deceleration. Means that when the electron react with the gas molecule, it can experience deceleration. So during the deceleration, this electron will lose its energy and create photon known as beam-Stirling effect. Next. So during the deceleration of the electron, it also can emit UV radiation that travel through the Geiger-Müller counter and create the avalanche effect at the other corner of the tube. So we can conclude that with only one present of ionized electron, it can cause Thomson avalanche effect along the entire system. So the ionized electron that is not decelerated will absorb by the anode, which is the center of the electron, will complete the circuit and causing a potential drop across this RR. So the potential drop is measured by the electronic switch that detect it as existence of the external particle. So this ionized electron will complete the circuit but come back to the surface of metallic tube.
Okay, so for the last part is the neutralization of ions. So from process A to E, the electrons deposited, not really deposited, but it is traveling from the anode to the cathode, right? So the neutralization is from for the positive and negative ion to recombine back. So it happens here, which is, you can see the green holes here. So the electron then will go through the outer circuit to the counter and go back to the metallic tube here and form neutral. So which means that it is the neutralization of ions. So this neutralization causes the Geiger-Müller to turn back into its original setup, which is the first one, which is the before it happens part A. Okay, and it actually takes a long time for the avalanche process to occur because it needs to be hit by the alpha, beta, and gamma particle. Then for the electron to accelerate and decelerate, and then to travel through the outer circuit. And during the avalanche process, there is a moment which we call the dead time, which is the Geiger-Müller tube will not detect either nuclear radiation that's coming outside. Okay, so what is actually that time? Okay, that time is a period of that the Geiger-Müller cannot detect other ionization. Okay, for instance, we have like three ionizing radiation, right? We have 1, 2, and 3, but only one of them that will be read by the counter, and not the second and the third one, even though it happens simultaneously. Okay, and the dead time happened during the entire process of the Thomson avalanche cycle and lasts about 200 to 400 microseconds. And as long as the circuit is not completed, the completed here means that as long as the electron from the anode did not travel up to the metallic tube back to convert it to the original form of the Geiger-Müller tube, the dead time will not stop. stop. Which means that the cycle is not complete. As long as the circuit is not complete, the Geiger molecular tube cannot detect any further nuclear particles or other non-sending avalanche process, which means that one cycle happens for one part of electron. Okay, so that then comes chronologically. First, it happens ionization, right? Ionization from the outer of alpha, beta, and gamma. Acceleration and deceleration, emission of UV radiation, detection from the counter, and the neutralization. So this picture is the magnified one. So the process did not just end yet when the neutralization happened. So during the neutralization, as we know, the electron will come back to the metallic cube, right? This is the metallic cube, and this is the positive ion that were produced during the ionization, and this is the electrons that come back from the anode to the outer circuit. So when it recombines, it will emit photons. The same thing as the emission of UV radiation, but this part is the UV radiation, and this part is the photon emission. So this photon emission will interact with the argon gas, and this is bad. So to prevent the photon emission to prevent it from creating another Townsend avalanche effect, so we need to quench it by quenching or external quenching. Okay, quenching is a process when the photon emitted. This is a photon emitted from the combining of positive and negative ions to be quenched or extinguished. So why does the quenching process important? Is because the photon is capable to start another avalanche chain reaction. So like the group first said, so the first time okay, from the first part, when the radiation enters, we already have the first counter, right? So okay, so when the photon emission have another the first UV radiation and the second one will produce another avalanche effect if it is not quenched, meaning that it will give two readings. Thus, this means the reading of the counter will be inaccurate. So, and also when the avalanche effect in the daytime, right? The daytime will not detect other ionizing radiation. So, it will cause the daytime to be longer and inefficient for the Geiger-Müller counter to read another reading for the ionization. Okay, so we have two methods for the quenching, which is chemical quenching and external quenching. So chemical quenching is the organic compound added to the gaseous medium, such as ethanol. So in this cube, we have 90% argon and 10% ethanol. So we add ethanol so that the ethanol will absorb the photon in the form of vibrational or rotational energy, and thus this preventing the avalanche effect that will extend the daytime of the Geiger-Müller. So another one is the external quenching, which the device itself will shut down itself for a moment. So the quenching is basically to prevent the extension of the Geiger-Müller daytime, because when it is dead, it cannot detect other reading ionization. Okay, that's all for me.
And then there's no rotation. So height energy will decrease. So it will induce the second ionization. So the electron will correct further, and then produce UV proton will be proton. And then it will, due to the acceleration of the gas molecule, so UV proton akan ini, and then create further collision between the electron and get the imbalance. And then proton, so electron can select one anon, and then if the signal in the output. So dekat dalam ni still have positive ion. So positive ion is actually more moving slowly than electron. So dia akan ada surrounding around the anon. So this is due to the tension moving slow compared to electron. So untuk